Good morning, class, and welcome to this lesson on Circuits 13, Capacitors and Circuits. Today, we will be able to calculate the equivalent capacitance of capacitors in series and in parallel. Okay, so we're going to be looking at capacitors in a circuit now versus resistors, or actually probably looking at both. Okay, so first thing, let's look at some capacitors in parallel. We have a capacitor here and a capacitor here. Okay, what we know about capacitors in parallel is that the voltage is going to be the same. This goes back to series circuits. The voltage is going to be the same through both branches here, okay? Through both branches here. And because the voltages are the same, so voltages same, the charge Q is going to add up. Okay, the charge is going to add up. So this capacitor will store a certain amount of charge. This capacitor will store a certain amount of charge. So the total capacitance is going to be, the total amount of charge is going to be the sum of both of these. And let me show you why. So we're saying that Q is equal to Q1 plus Q2. Okay, Q1 plus Q2, as in the charge on this plate plus the charge on this plate. Well, we know that Q equals CV. So C1V plus C2V, okay, equals Q. And we know from this that V is constant. So the charge is equal to C1 plus C2 V. So what we see from this equation right here is that the capacitance is added up for the charge. So our definition here is going to be the capacitance in parallel is equal to the capacitance of each capacitor added up. The capacitance in parallel is equal to the capacitance of each capacitor added up. Okay, and you can see that from this right here. Here is a capacitor in parallel. If we break it down into both of them, so we added both of them up, we add the charges from both capacitors and we add them up. So the capacitance will increase when capacitors are in parallel. Same voltage, charges add up. Okay? Now in series, what we know is that let's just say the voltage here is 10 volts. We know that these if these were resistors, the voltage would add up to make 10, right? I'm just making numbers up right now, but it would add up to get 10. So the voltages are going to add up. So the total voltage equals V1 plus V2. Well, Q equals CV. V equals Q over C. So V is equal to Q over C1 plus Q over C2, etc. In a series combination of capacitors, in series, Q is constant, and voltage adds up. Okay, Q is constant, voltage adds up. So Q is constant right here. Q is the same thing, so it's going to be Q 1 over C1 plus 1 over C2. Okay, this is eventually going to give us 1 over the capacitance in series. So if we want to know the capacitance in series, it's going to be 1 over CS, CS being in series equals 1 over C1 plus 1 over C2, etc., 1 over C3. So the capacitance in series will actually decrease. So we will actually store less charge in series than we will in parallel. In parallel, the capacitance increase. We store more charge in parallel because we have the same voltage going across each one. In series, the voltage is split up. So the total capacitance goes down. So in series, the capacitance goes down. So you're probably seeing a pattern here. Resistors in series is just like capacitors. It's similar to capacitors in parallel. Okay? R1 plus R2 plus R3 is kind of the same as C equals C1 plus C2 plus C3. So on the flip side, resistors in parallel is kind of like capacitors in series. 1 over R equals 1 over R1 plus 1 over R2, etc. This is similar to 1 over C. S equals 1 over C1 plus 1 over C2, etc. Okay? So capacitors are kind of like resistors, but they're flipped. Okay, so the capacitance will go down in series and it will go up in parallel. We can store more charge in parallel than we can in series. Now I'm just going to give you a couple more small tips with capacitor problems. Okay, you're going to see a lot on tests or questions, and it's going to say this circuit was closed for a very long time. For a very long time. Okay? And it's kind of like, why is that there? Why does that matter? So let's just say we have a circuit here, battery, and then we have a capacitor here. And I'm going to fix this here. I'm going to put a switch right here. So we have a switch that's open right here. And we're going to say the circuit was closed for a very long time. So basically we closed the switch for a very long time. What this is telling us is that for over a very long time means the capacitor is fully charged. The capacitor is fully charged because capacitors take time to charge up. Think about when you take a picture. It takes time for the capacitor to charge up again so you can have another flash in a picture. Well, same thing. This capacitor is fully charged because it was closed for a very long time. Okay? So that's one tip, okay? Another tip, and on the same note, I'm gonna draw the same circuit here, but I'm gonna draw it a little bit more advanced. Okay, and let's say there's a light bulb right here. Okay, a light bulb. And let's say the circuit is closed, the switch is closed, and we'll say, once again, we're going to say the capacitor or the circuit was closed for a very long time. What would happen to this light bulb here? And this light bulb would be dead. It would be burnt out, or not be burnt out, but it would be off. The light would be off. Why? The light would be off. Because once a capacitor is fully charged, there is no more current. There is no more current. Okay? There wants to be a current, but the battery can't push any more charge onto this plate. So once this thing becomes fully charged, there is going to be, a positive side and a negative side waiting to be discharged. And until it gets discharged, there's going to be no current going on this branch right here. Okay, this branch will still work just fine, but this branch will have no more current passing through it. Okay, so the current is now done. Okay, and last but not least, I've seen some problems like this as well. Where we have something like two switches. Okay, and we'll call this S1 and S2. And the question says something along the lines of, what's going to happen after a very long time if both switches are closed? So we close both switches. Okay, we close both switches. After a very long time, we know the capacitor is going to be fully charged and the current is going to be going through this direction right here. Okay, that's not a big deal. And then the next question will say something like, what happens if we open up S1 but close S2? What happens if we open up S1 but close S2? So basically we disconnect the battery and the capacitor is still fully charged. Okay, so the capacitor is fully charged and then we disconnect the battery. And what's going to happen here is over a certain period of time, we're actually going to see the capacitor discharge. The capacitor will discharge. Because the battery is like the pump that keeps the charge on the plates, okay? The battery is like the pump that keeps the charge on the plate. But once we disconnect the battery, and there is still a circuit here for the capacitor to move, if there's still a circuit here, what we'll see is that the electrons that were stored on this plate are actually going to go back, and it's going to equal out again. Okay, so those are just some small things that I've seen through capacitor problems that you want to look out for, because you might see it in a problem and go, wait, what's going on with that? Okay, so that's it.